Okay, we are going to do an example where we find critical points for a system of differential equations. We find the x nullclines and the y nullclines, and then from that information, we sketch a plausible phase portrait. Okay, well, first we should find the critical points, or in this case, I call them fixed points, it's the same thing. The critical points are where x dot equals 0 and y dot equals 0 simultaneously. And those things happen at the same time. Well, for the equation for x dot, in this case, it's x minus x cubed. If we set that equal to 0, I can rewrite this by factoring out an x and write this as x times 1 minus x squared. This expression will be 0 when either x is 0 or when this factor is equal to 0, and that happens when x is plus or minus 1. On the other hand, if I look at the y dot equation, y dot is equal to negative y, that is equal to 0 when y is 0. My critical points then are all the combinations of these simultaneous values. So I have one when x is 0 and y is 0. I have another critical point when x is positive 1 and y is 0. That's that point. And then I have another critical point when x is negative 1 and y is 0. That critical point. Now we want to sketch the x nullclines and the y nullclines. The x nullclines are the curves along which just this equation is satisfied. So when I'm not worrying about the other equation, I just want to satisfy this equation and sketch those curves. Well, if I just look at the first equation, these are my results. X is 0, x is negative 1, x is positive 1. Y can be anything. So these are vertical lines along the values x equals 0 and plus or minus 1. So if I go over into my, my graphs here, I want to sketch the line negative 1, x equals negative 1, x equals 0, x equals 1. So this is x equals negative 1, x equals 0, x equals 1. Right? Y can be anything. The critical points are actually the intersections of the x nullclines and the y nullclines. In this case, I'll sketch them on the plot here just for completeness. The critical points are at negative 1, 0, 0, 0, and 1, 0. Those are the points where y dot and x dot are 0 at the same time. The x nullcline is just when x dot is 0. Now, from this information, we can actually decide, or we can figure out what's going on with the x variable to the left of the nullclines and to the right of the nullclines and in between. Well, when we're on the left of this nullcline, x is less than negative 1. And we want to ask, well, what's happening with x of t when x is less than negative 1? We can figure that out by maybe choosing a value for x less than negative 1, say x equals negative 2. Then x dot is going to be negative 2 times 1 minus 4. This is a negative value times a negative value. So we have a positive value. Therefore, in this region, x dot is positive. In other words, x is increasing. So x is going to the right. We don't know whether our trajectories are going to the right and down, or, to the right and down, or to the right and up. But we know that they are going to the right in general. Okay, I can even, let me just like shade this region because it's this entire region where x dot is positive. Then we can test a point in this region when x is between negative 1 and 0, say when x equals negative 1/2, then x dot would be something like negative 1/2 times 1 minus, x dot would be negative 1/2 times 1 minus 1/4. This term is positive. This is negative. So I have a negative value here, meaning that my trajectories are moving to the left in this region. So in this entire region here, my trajectories are moving left. And you could check other points in these other two regions. Say like you check x equals 1/2 in this region and x equals 2 in this region. You would find that our trajectories move to the right in this region and to the left in this region. So trajectories are going left in that region, right in that region. Along the nullclines for x, along the curves where x dot is equal to 0, the trajectories are not going left nor right, meaning they are going exactly up or exactly down. Okay, now we can look at the y nullclines. These are the curves along which just y dot is equal to 0, and we don't really care about x dot at the moment. Well, the curve along which y dot is equal to 0 is just the constant function y equals 0. That puts us exactly along the x-axis. This is the curve y equals 0 for every x value. Our critical points are still at -1, 0, 1 along the x-axis. And notice that those points are exactly the intersection points between the x nullclines and the y nullcline. It's exactly these 3 points. But for the y nullclines, we just want to also sketch what's going on with y of t. Above the y nullcline, this is the situation where y is greater than 0. Y dot is negative y. So when y is greater than 0, negative y is less than 0, and y dot is then negative. So my solution should be moving downwards in this region. So let's sketch that. I'll use like a teal color here, downwards. And we'll highlight this whole region. In this region, our trajectories are moving downwards. Y dot is negative. And then similarly, when y is less than 0, say y is like -5, negative y is positive. So -5 gives me a +5. So my trajectories are moving upwards. Let's do this in like a purple color. In this region, the trajectories are moving upwards because y dot is positive. Now to sketch a plausible phase portrait, it's not exact, it's just a sketch. We're going to combine these two situations. So let's sketch, just briefly sort of outline the nullclines here. I have this nullcline, the x nullclines are these vertical lines. And the y nullcline is this horizontal line here. My fixed points are still the same. They are still at -1, 0, 0, 0, and 1, 0. But now I'm going to sort of label things based on my x and y nullclines. In this region over here, I know that my solutions should be moving to the right. In the region next to this, they move left, and then they move right, and then they move left. In the entire upper half plane, my solutions should be moving downwards. And in the entire lower half plane, the solutions should be moving upwards. So what I want to do over here is combine all of these behaviors. In this region, I want to combine a rightward motion with a downward motion. So my trajectory should be doing something like that. I don't know, from this analysis, I don't know if they're doing this or that, but I know they're going down and to the right. So they're doing that. I also know that they should be approaching this critical point. So maybe I can sort of show that they're approaching that critical point in that way. In this region, my trajectories are moving to the left and down. So they're doing something like this. I'm not sure exactly if, the concavity of how they're approaching, but I know they're going down and left and towards the critical point. Next, I look at this region. Oh, sorry, I did it again. This region, my trajectories are moving to the right and down. So they're going towards the critical point, something like that. And then in this region, I have left and down, and so towards this critical point in some fashion like that. Okay. I can do the same thing in the lower half plane, except now that the trajectories are going up. So say in this scenario, I am moving left, like this is a green region. I'm moving left and up because I'm also in a purple region. So left and up. Sorry, they're moving to the right and up, excuse me. My arrow is pointing to the right in this green region and pointing upwards. So to the right and up and approaching that critical point. In this region, I am moving to the left and up. So something like that. In the next region, to the right and up, to the left and up, something like that. Again, from this analysis, we don't really have the concavity. These would be curved somehow, but we don't necessarily know what that's going to look like. So I can just plot these. We do know that we should be moving away from this point. So you could think that they sort of do this potentially, but in any case, this is perfectly reasonable answer. And that's the end of this problem. So let me know if you have any questions.